Hello everyone, my name is Jacob Stolle, and today what I want to do is discuss a research program, and particularly one project looking at the response of wood structures under hydraulic loading as part of a larger program that was initiated in collaboration between the University of Ottawa and TU Braunschweig, examining the response of structures under extreme wave loading. So you can see an example here to give a kind of an idea of our motivation. This is a video from the 2011 Tohu tsunami, where you see a lot of large construction material, full buildings that have gotten picked up and trained within the flow and are interacting with structures, causing downstream effects which aren't necessarily captured through physical, can't necessarily be captured through physical and numerical modeling. And what I'm talking about in specific is what's generally called second order effects. So these are the consequences of consequences. So if you think of first order effects, it would be things like hydrodynamic scour, where they're consequences of a particular hazard, in this case, an extreme flooding event. Consequences of consequences would be examples like the 2018 flu Indonesia tsunami. So this is an example where you had a hazard, an earthquake, which generated a landslide, and those landslides generated tsunamis. You can see an example in the top right here of a wave generated by one of the landslides off the coast of Blue Bay. And the ones that we tend to deal with, particularly within tsunami engineering, is second order effects of the built environment. So these have been outlined in the ASC 7 chapter 6. There's things like shielding. So this is when a large structure, so this in this case would be a positive secondary effect. Second order effect, where you have a large building which protects other structures behind it, channeling of flow, so you get an increase in the momentum of the flow due to this kind of contraction of the flow channel. And the one that kind of brought us to this area, which is debris. So these are, so you can see some examples of debris here on the right. There's a warehouse in Bamborough City, essentially where because of this kind of snowball effect of debris getting picked up within the warehouse, subsequent downstream onshore structures were destroyed because of this accumulation of debris. Second example would be both these examples actually were where walls or retaining walls in front of these structures got destroyed. The rubble was picked up as debris and impacted structures. And what we noticed is it's very difficult to capture these type of effects, particularly in a hazard assessment scenario. So we wanted to develop a research program that looks at how we can address these second order effects in a built environment. So in terms of what we wanted to look at first is we wanted to develop methodologies for modeling realistic model structural behavior under debris and hydrodynamic loading to look at how these buildings would fail, how they generate debris, and how can we incorporate that into hazard assessment models. And in terms of the short-term objectives, which I'm going to discuss here, is what we want to do is examine how simplified structures behave under extreme wave loading, and develop a comprehensive data set that we can use to start initiating physical or numerical modeling efforts. So the tests themselves took place in a large wave flume at the Coastal Research Center in Hanover, Germany. So it's a 306 meter with a 7 meter by 5 meter cross-section flume. Large wave flume, we used a hydrodynamic boundary condition of solitary waves. We used 3 different wave types: 0.5 meter, 0.8 meter, and 1.1 meter. Waves, which essentially would propagate over the flat section, would shoal and break on the slope, 1 in 14.5 slope, and propagate over land. We had ultrasonic wave gauges monitoring the change in water depth, ECMs monitoring velocity. We also did large-scale particle image velocimetry to capture the flow velocities, particularly within the wavefront, where it was difficult to capture with ECMs. The structure itself was a simplified wooden square column, 0.3 by 0.3 meter cross section, 0.8 meters tall. We varied the construction a little bit changing the thickness of the plywood and also the number of nails within the joints, kind of change rigidity of the joints. And we monitored the response of the structure using accelerometers. So you can see we looked at 5 different types of structures. We varied the thickness of the plywood. We varied the number of nails. And we also had a rigid structure to serve as our reference case where we could measure things like pressure, things where if we weren't worried the building would be destroyed, we could leave all the instrumentation around the structure. We also did a single input, multiple output using a hammer to capture the natural frequencies of the structure, of the different structures. And you can see there are slight differences in terms of the natural frequencies of the structure. And just to give you an idea of the hydrodynamic conditions, the broken solitary wave, relatively what we would expect. There's a slight bump here related to just kind of the bed topography. And then the large scale particle velocimetry, we can see the kind of gradual decrease in flow velocity over time. And here you can see an image, exactly what we'd kind of expect from this extreme wave event. You get the initial wave impacting the structure, the initial splash up, the formation of the standing roller in front of the structure, and formation of the wake. But what we wanted to focus on, particularly within this study, is looking at the structural response. So I'm going to show the structural response for all the different structures, but first I wanted to kind of work through this graph because there is a lot of information presented all at once to give you an idea of what we're actually looking at. So in red in the top panel is the time history. So between the wave arrival, which occurs around 3 seconds, you can see the spike in force there. So the red is the global forces over time. The black is the acceleration response. So that's measured. This is only looking at one of the nodes located at the top of the structure. So you can see the acceleration response matched with the global forces. And then below here is what we have a spectrogram, which is looking at the frequency response of the structure to the forcing condition. So here, essentially, we're doing short time interval, fast Fourier transformations, and getting an idea of the strength of the signal over time, over the length of the test. So you can see the wave arrives here, and then you start to see the actual response of the signal, which matches well with the acceleration signal, which is what we're actually decomposing. We also plotted the natural frequencies of the structure. So you can see it's the red dashed lines, just to give you an idea of what the natural frequencies of the structure were. And then also to give you an idea of how kind of the general trend of the structure, you have the cumulative response. So this is kind of taking that spectrogram, combining it all into a single data plot. This has been kind of blown up, so you can see it correctly, but you can see two clear peaks closely related with the natural frequency of the structure. And just to give you kind of general idea of what you typically expect within these spectrograms throughout a wave event. So essentially you have, and where that initial impact occurs, you get the saturation of the signal. Kind of generally, it's actually throughout the whole frequency domain. It's very similar to kind of an impact type loading event, where you'd expect that saturation, kind of the theory behind using a hammer test. And as we move away from that impact event, what we see is the response of the signal tends towards the natural frequencies of the system. So you can see in this case, they're slightly off. They should slightly damped, probably because there are nonlinearities in the structure. Also, there's a lot of damping as a result of the hydrodynamic conditions. And this is kind of what we would expect. There's been other studies by Zhang in 2020, and Omarasi did a lot of work with Kaisan breakwater. And we expect kind of this, after the initial impact of the wave, we're getting this this oscillation related to the natural frequency of the structures, which can be important in addressing things like base shear of structures, because that is going to be your main frequency of motion. So now looking at kind of the full matrix, looking at a bunch of different structures and a bunch of different wave heights. So if we go down along, so there's the same figure as the slide before, but what you get is, as we move down here, this is increasing wave height. And as we move across the row, we get different structures. So for here, again, we're only looking at 3 structures, one of the 20 millimeter plywood, and then we're looking at 4, 7, and 10 nails. And then again, we're looking at 0.5 meter, 0.8 meter, and 1.1 meter wave heights. And then you can see this full matrix. So the figure that we just saw is actually the one in the center here. You can see it's exactly the same as the figure before. And again, so we have the spectrogram, force signal, and the acceleration plotted all kind of for one set of experimental tests. And what we see kind of across the board is we do see that general behavior that we would expect. You get that initial saturation of the signal as the wave impacts the structure. And as we move into kind of the quasi-steady tail part of the flow, most of the motion of the structure is related to the natural frequencies of the system. But what we did notice is as you start to increase the hydrodynamic forces, what you see is there's actually a shift from kind of a mixed modal response of the structure. So you can see in the case of 0.5 meters for the plywood thickness of 20 millimeters and the number of nails of 4. You have this mixed modal response when you have the smaller wave height. And as you move into stronger and stronger hydrodynamic forcing conditions, what you see is that mixed modal response tends towards the first bending moment, or the first natural frequency, which in this case is the first bending moment of the structure. So kind of as you expect, as those higher modes tend to get damped out by the first bending moment. And what this gives is a kind of an idea of what exactly we need to look for when we're modeling structures in these extreme events. Can we simplify it using just the first mode, modeling just based on the first mode to get an idea of what their response would be and what their potential failure modes would be? But there's still a lot of work to do. And what we did here is just we looked at how structures respond under broken solitary waves. And we saw that the response to the structure was dictated by the hydrodynamic loading conditions. And there's potentially an area for simplifying how we design these structures in the model in a model in these extreme wave events by using just the first bending moment. So in terms of next steps, what I want to do is we now want to kind of look at further and look at how structures fail, and can we use this same modal analysis to do this type of thing. And we also want to develop methodologies on how we can model these structures, how we can correctly model a response to the structure under wave loading. So you can see here a video. This is from the same test series using a different type of structure. But this is one where the structure actually fails, gets washed off its footing, and propagates downstream kind of as we saw in the video at the start. So here are my references, and I'd like to thank you for listening. And if you have any questions, feel free to ask.